this set of notes, we're going to continue our discussion on assessing model adequacy. In particular, we're going to talk about outliers and how to identify influential observations. So when assessing model adequacy, it's important to check for outliers, leverage points, and influential points. And so let's start out with just a couple definitions. So an outlier is a data point whose response Y does not follow the general trend of the rest of the data. And a data point is considered to have high leverage if it has an extreme predictor X value. Now with a single predictor, an extreme X value is simply one that is particularly high or low. With multiple predictors, extreme X values may be particularly high or low for one or more predictors, or it may be an unusual combination of predictors. And then a data point is influential if it unduly influences any part of the regression analysis, such as predicted responses, estimated slope coefficients, or the hypothesis test results. Outliers on high leverage data points have the potential to be influential, but we generally have to investigate further to determine whether or not they are actually influential. And so this is one of the reasons it's so important to determine if you have outliers or high leverage points, is because it may be that these data points really aren't having any effect on your analysis and we don't have to be concerned. On the other hand, if they're influential, then that could be of concern. So outliers can usually be attributable to one of several cases. And so the first one is the measurement with the outlier might be invalid. And so this can happen for several reasons. It might be that the machine that was measuring the response, something happens. It might be that a data point was just simply entered incorrectly. Or it could be that they were coded incorrectly. And this can commonly happen with categorical variables. Because remember, for categorical variables, we often enter them as numeric into the data set. And so accidents can happen. Now when outliers are due to this, we can change them in the data set, but we have to document any changes that we make. So for example, if we know that when entering the data, a value that was supposed to be 10 was accidentally entered as 1,000. We can go ahead and change it, but we do want to document somewhere and say, hey, originally this was entered as a 10, originally this was entered as 1,000, it should have been a 10, so we have changed it back. It's all about transparency and documentation with anything that you do with the data set. And so in cases like that, it would be okay to change it, we document, and then we move on with our analysis. But in other cases, it's not okay to remove the outliers. And the reason for this is outliers may be giving us important information about what's happening in the underlying population. This can particularly happen when our population is skewed. So one way to think about it is when you have a skewed population, if we think of the tail that's in the direction of the skew, there's not a whole lot of observations there. There's not a whole lot of pieces of the population in that tail. So it's likely when we go to sample that we might only get one or two pieces from that tail in our actual sample. And so at initial inspection, it might say, well, that observation seems really extreme. There's only one of them, but really it's telling us a valuable piece of information. So we need to consider these things. Outliers may also be a result of an omission of an important independent variable or higher order terms. So this is another way that we can use these to help us assess the fit of our model. It may be that the model we chose isn't necessarily the best, and there may be another one that we could choose that we won't have outliers for. So it's just something to consider. Now there are several formal techniques we can use to identify outliers and points with high leverage. We're going to look at just a couple of them. But do know that there are other ones, and I'm going to have you look at a couple additional ones in the practice problems for this module. So the first technique that I want to look at is what is called the standardized residual. So the idea of a standardized residual is we make the assumption that the residuals are normally distributed. So in other words, if I could look at all the residuals, they'd follow a nice normal distribution. And just for ease, I'd like to be able to compare them to a standard normal distribution. Now we already make the assumption with our residuals that they have mean 0, but in order to get them to have standard deviation 1, we work with the standardized residuals. In other words, this value right here. So notice that we take the residual and divide it by the standard deviation. And if you'll recall from the module 10.2 notes that the standard deviations of the residual is equal to the standard deviation of the fitted regression model. So this transforms this to a z, which does follow a standard normal. Now, one of the things that you learned in your intro stat course was what is called the empirical rule. And if you'll recall, the empirical rule tells us that if we have a standard normal curve between -3 and 3 is 99.7% of the observations. So for this reason, what we're saying is if we end up with a standardized residual greater in absolute value than 3, that would be unusual because we know majority of the data should be between there, and so that's evidence that that could be an outlier. Now, this is just a general rule of thumb. One thing to keep in mind is if I had 1,000 data points and I end up with one standardized residual of 3.2, that really wouldn't be unusual because with 1,000 data points, I would expect a few of them to fall in these tails. Now, of course, if I have 1,000 data points and I end up with a standardized residual of 102, then no matter what, that one's going to be unusual. So these are things to keep in mind. With any of these guidelines we look at, they are just general rule of thumbs, but we do want to think about where they come from, and we want to critically think about the values that we are comparing them to. Now, the other thing that I do want to note here is that SAS refers to the standardized residual as the studentized residual. And you can read about that here in the SAS documentation, and you will see it's the same value that we have here. This can be confusing because other texts define the studentized residual slightly different, and you'll notice here the difference is here in the denominator. So I put that here for your information just to be careful that if you are using the studentized residual in SAS, that studentized residual might be different from another piece of software. So this is one reason that it's really important that whatever software you're using, it's always a good idea just to double check the documentation and make sure that the thing you're calculating really is the thing that you think it is. And again, this goes back to that idea of reproducible research. So if I'm going to report that I'm calculating, studentized residuals, but I'm pulling the studentized residual from SAS, that's really what's more commonly referred to as the standardized residual. So I want to be careful about these things when I report them. So if someone reads my report, they would know, okay, that's exactly what they calculated, so I can go and reproduce this. So I might say that I'm reporting the studentized residuals from SAS. And then someone will know, okay, if I pull a studentized residual for someone else, it might not be exactly the same as the one they're getting, but if I know if I use SAS, I will get this. So again, it's all about this idea of transparency. Now, the values that we are going to look at, we are going to look at the standardized residual. This is going to help us determine outliers. We're going to look at the leverage HI, and this is going to help us identify points that have high leverage. So we're going to be looking at this value. We're also going to be looking at Cook's distance. So Cook's distance will actually help us look at a measure of overall influence of the outlying observation. So we do need to first see if it is an outlier. And so a large value of Cook's D is going to indicate that the observed value has a strong influence. Now we're not going to use Cook's D by itself to determine influence. We're also going to look at some of those other things that we talked about earlier. But just keep that in mind. Alright, so what I'd like you to do now is I'd like you to pause the video. I'd like you to take a moment, read through these different values, get a feel for what we're going to compare them to, how they're used, and then we're going to look at an application of these to a data set when you come back. Alright, now that you've read those, we're going to look at an example. What we're going to do is we're going to start out with a data set that has 20 points in it. And then we're going to systematically add in a 21st data point, and we're going to see what happens to the regression model based on, does that point have high leverage? Is it an outlier? Those types of things. So we're going to start out here with the first data set. This is the one without an additional 21st data point. So this one is only going to have 20 data points. So looking here at the scatter plot, we can see we've got a nice linear positive association. None of the points look unusual. Everything kind of flows in that nice straight line. So some values that we're going to compare later on that I want to bring your attention to is we have the overall f-test. We have r². We also have the intercept, and we have the slope. So we're going to use these for comparison later on. also want to bring your attention to the output in terms of the residuals. So notice here, this column right here, these are going to be your yi's. Here is your y hat i's, the predicted values, and then here are those residuals. And then our three criteria we're going to look at are the standardized residual, Cook's D, and the leverage. So I've highlighted these here. So let's look at these for our initial data set. So the first thing we're going to look at is the standardized residual. And remember here we're looking for anything that has value greater than 3 or an absolute value of 3. So looking down through the student or the standardized residual, we see that none of them are greater than 3 in absolute value, so we have no concerns. Now for the leverage, we want to compare to this value here. So we're going to have 2 times k plus 1. This is simple linear regression, so k was equal to 1, and then we had 20 data points, so this is equal to 0.2. So looking at leverage, kind of scrolling through here, we don't have anything greater than 0.2, so we don't have any concerns about a high leverage point. And then for Cook's D, what we compare to is if we were to draw an F distribution, what we're saying is we want the endpoint that has 50% of the area to the left. And then recall for Cook's D, the first degree of freedom was equal to k plus 1, which in this case is 2, and the second degree of freedom is equal to n minus k plus 1, which in this case is 18. So you'll notice here is the R code to find that endpoint, and this is very similar to what we did at the beginning of the semester. And so the value of Cook's D that we're going to compare to is this value right here. So looking through the Cook's D values here, notice that none of them are greater than that 0.2. Oh, actually, I take that back. We do have one. Sorry, Cook's D, we're comparing to 0.72, not 0.2. So comparing to 0.72, we don't have any values that are greater than the 0.72, so we don't have any concerns with Cook's D. And we anticipated this. When we looked at that scatter plot, it didn't appear that we had anything that was an outlier or high leverage or influential. Everything fell kind of in that nice line. So this is why this is going to kind of be our base case. This is going to be our starting data set with our 20 points. And now what we're going to do is we're going to add in a 21st point and we're going to see what happens. Alright, so looking at data set 2. So for data set 2, we're adding in this new data point. And here's where the data point is on the scatter plot. Notice that this point looks unusual compared to the rest of the data points. And so we're first going to try to figure out, is this an outlier? Does it have high leverage? And then is it influential? So to determine the influential part, we are going to need some output from data set 1. So these are those values that we had highlighted up there earlier. Here is the output, but before we look at this, let's first determine if we have an outlier or something with high leverage. Alright, so here's our 3 values. First thing we're going to look at is our standardized residuals. So looking at the standardized residuals, remember we're looking for any values that are greater than 3 in absolute value. The other thing to notice here is since we added in that 21st observation, we know that our regression line is going to change slightly because we've added in more data, and so because of that the residuals are going to be slightly different than what they were for model or for data set 1 rather. But looking through here, we do see that our new data point, notice this is our 21st observation, does have a standardized residual greater than 3. So this tells us that our data point 21 is an outlier. Next, we're going to look to see if we have any evidence of high leverage. So to do this, again, we first need to calculate 2 times k plus 1. K is still equal to 1 here. We fit the same model. But now we have 21 data points, so that is going to change our comparison value just slightly. So we're going to have 0.1905 that we're comparing to. So looking through our leverage values, we're seeing if any are greater than 0.19, and looking through we see that none of them are, so we don't have any concerns here. And then finally for Cook's D, again, we're looking at that F distribution where we have 50% of the area to the left of the endpoint we're interested in. This time we're going to have 2 degrees of freedom in the numerator and 19 in the denominator. So here is that R code. So this time we're going to compare to 0.719. So now looking at our Cook D values, again, notice that none of them are higher than the 0.719. So Cook's D doesn't suggest that anything is influential. Now, we did have an outlier per the standardized residuals, so let's go and look and see if our regression analysis changed very much based on the presence of this outlier. And to do that, we're going to compare our original output from data set 1 to our new output with our second data set. So first of all, previously we had that the F-test was significant. Notice here our F-test has slightly changed, but it is still significant, so we end up with the same final result. We see that our R squared has dropped a little bit, but it's still pretty high. And then if we look at our slope and our intercept, they are close. They're not exactly the same, but they are close to what we had before. So, and in particular looking at the slope is very close to what it was before. So even though we have an outlier in this case, we would not say that that outlier is influential. Because again, we added a new data point. We expect some fluctuations in the regression analysis, but our overall analysis is very similar to what it was before. All right, let's do the same thing, but look at a third example. So now we're adding in a different 21st data point, and notice this time we're adding in an observation all the way out here. Now before we go through and look at whether or not this is an outlier, what's happening here, let's talk about whether or not we anticipate this to be influential. So when we talk about something being influential, we're saying that it's going to change the regression analysis. Notice all of our original data points are in this region here. If we were to fit a regression line through this, it's reasonable to say the regression line would look something like this. Notice that that new data point follows right along with that trend of where that regression line would go. So intuitively looking at this, we should not expect this to be influential. And again, because that data point occurs on the path of where the regression line would probably go anyways, I'm not going to anticipate this to be influential, but we do always want to check and see what the data tells us. And so let's do that. Again, here I have our original regression analysis from the first data set, so we'll compare that later on. But before we do that, let's first look at our residuals. All right, we're going to start out with the standardized residual, just like we did before. And again, we're trying to figure out whether or not we have any that are greater than 3 in absolute value. So looking through here, notice that none of them are, and that's including our new data point. So this is not considered to be an outlier looking at the standardized residuals. Now let's look at the leverage. So remember again, we're going to compare to 2 times k plus 1 divided by the number of data points, which is still 21, so we're going to compare to 0.1905. Looking at H, notice that our new data point does have high leverage. So here's an example where it's the opposite of what we saw last time. This data point isn't an outlier, but it does have high leverage, so we're going to need to see if it's influential. Now, let's see if it's influential looking at Cook's D. So we found Cook's D, our cutoff point, just like we did in the previous example. So we are going to be comparing to that 0.719. And notice that by Cook's D, this one is not considered influential. Now the Cook's D is, pretty close, but it doesn't meet that cutoff. So let's go up here and look at our actual regression analysis and see if this looks like it was influential. So we're going to compare some values here. First thing, let's look at our overall F-test. Notice the overall F-test is still significant. Our R-squared value is very close to the original data set. In fact, it's even closer than it was when we looked at the comparison between data set 2 and data set 1. And then if we look at our slope and our intercept, same thing. The slope and the intercept are very similar to what they were before. So we're not seeing large changes in our regression analysis, even though this point had high leverage. Okay. So again, kind of recapping, we looked at data set 2. We saw an example where we had an additional data point that was an outlier, didn't have high influence. This one, we're seeing an example of a data point that has high leverage, but still does not have influence, or it's not an influential point. So let's look at one more example. We're going to look at data set 4. So now our new data point is here, and we can see it occurs all the way down here. This one definitely looks unusual. And if we think about where our original regression line was, we can imagine that if we added in this new data point, that a new regression line refit is probably going to be pulled in the direction of that point. And so let's see if that actually happens, if that's what intuition tells us. So again, for purposes of comparison, we have our output from data set 1, but let's first look at those residuals. Alright, so first thing we're going to do we have a standardized residual greater than 3 in absolute value? And so looking through here, we sure do, and that is our new 21st data point. Do we have high leverage? And remember we saw before that we're comparing this to 1.905, I do believe. And we can see that yes, we do. So we have a data point that is both an outlier, it has high leverage, and so now the question is, does Cook's D say it's influential? So again, we're comparing to this value, and we can see based on Cook's D, this is an influential data point. So let's go and look at our regression analysis and see what changed. Alright, so we're going to start out with our overall F-test. Our overall F-test is still significant, but we do see a really big change in that test statistic. Look at your R-squared. Your R-squared is almost half of what it was with the original data set. This is where we're really seeing a drop in our regression analysis here. That is a huge drop in R-squared, and so this point is definitely influential. And then finally, if we look at the changes in our slope and our intercept, those are also fairly large. But the main place here that we're seeing is that R-squared value. That's where we're really seeing a big change in our regression analysis. So again, this point is not only an outlier, it not only has high leverage, but it is also influential. Alright, so the next 2 pages I'm going to have you read in your own. These are a summary of all the things that we just talked about. So you've got all those summarized right there for you. The last thing we're going to look at in this note set is what is called detecting residual correlation. It's called the Durbin-Watson test. So we do assume that our residuals are independent of one another. That's one of the assumptions that we make. Most of the time that is violated is when we look at time series data, or if observations are made on the same person, multiple times, which again, that would suggest time series because we're taking, multiple data points throughout time. So correlation of the error terms frequently happens when the data set is in a time series. In this case, the data is observed over time. Regression models of time series may pose a serious problem because the value at time t is often indicative of its value at time t plus 1. So in other words, they are correlated. And so you end up with correlated error terms, which is a violation of the independence. So you could have what are called positive autocorrelation and negative correlation. And then we have what's called the Durbin-Watson test statistic to test for the presence of residual correlation. Now, the problem with always relying on the Durbin-Watson test statistic is that this test statistic works if your observations are entered in time order. If there isn't a time order, then this test statistic really isn't helpful. So it's just something to keep in mind. If you take longitudinal data analysis, you would talk a lot more about time series and how to handle these. And this is going to end this note set.